Let's talk about pressure. So you may think you know what pressure is, but just hang in there with me a second. Pressure is a force per unit area. So, okay, well, I know that. Mathematically, it is defined as the limit of an area, as the limit of an area shrinks to that of a point of some normal force over that area. Okay? So for static fluids, pressure is always exerted on solids as a normal force or a normal pressure. With moving fluids, we have other pressure effects, shears and that sort of thing, but that's not extremely relevant for this course. So we'll stick to this definition. Unless stated otherwise, pressure refers to absolute pressure. Making a mess. All right, so we define absolute pressure as the pressure with respect to that of a complete vacuum. And of course, the pressure in a complete vacuum is identically zero. Absolute pressures cannot be less than zero. We can't have a pressure that is lower than that of a complete vacuum, which is zero. Gauge pressure is different. Gauge pressure refers to the difference of the absolute pressure of a substance and the absolute pressure of the atmosphere. Okay? So, P gauge is going to be equal to P of my substance, or whatever it is I'm referring to the pressure of, the absolute pressure of that minus the absolute pressure of the atmosphere, and we just denote that by P ATM. So to provide you an example of gauge pressure, so we measure the pressure in automobile tires or bicycle tires as a gauge pressure. So say you fill your tires up to 30 psi, 30 pounds per square inch. 30 psi with respect to a complete vacuum would be far too low. All right, so the atmospheric pressure is about 15 psi. So the absolute pressure of a 30 psi filled tire would be 30 psi, okay, plus the atmospheric pressure. That'd be the absolute, roughly 45 psi. So a zero tire pressure, as we would refer to it in everyday life, zero tire pressure means that the pressure inside your tire has the same pressure as the atmosphere. All right, so now with some clear space, let's talk about the units of pressure. All right, so we said before that the SI standard is a Pascal. And that is, of course, equal to 1 Newton per meter squared. Okay. But so there's some other very convenient units of pressure that you will see throughout the course. Perhaps the most widely used in this course is the kilopascal, and 1 kilopascal is equal to 1,000 pascals, or 10 to the third newtons per meter squared. All right, the next one is a bar. 1 bar is 10 to the fifth newtons per meter squared, or 100,000 pascals. The next one is a megapascal, or 1 million pascals, and that is simply 10 to the sixth newtons per meter squared. Okay, so when referring to atmospheric pressure, we often refer to atmospheric pressure as atmospheres. So, 1 standard atmosphere denoted often as an ATM is equal to 1.01325 times 10 to the fifth pascals, or we'll call it newtons per meter squared. It is equal to 14.696 psi, pounds force per square inch, and is equal to 760 millimeters of mercury, which we'll describe what this unit means here in a bit. Now, the standard atmosphere, or the value of 1 atmosphere, is constant. It is fixed in scientific practice, although the actual pressure of the atmosphere will vary across the Earth, and it will vary based on temperature and weather conditions and that sort of thing. Okay, so now we've talked about units of pressure. Let's talk about how we measure pressure. So barometers and manometers should be an E, are common, traditional pressure measuring tools. I say traditional because nowadays we've got electronics that can measure pressure instantly and in very small packages. But before the advent of these particular pressure gauges and sorts of things, we had barometers and manometers. So let me give you an example of what each of those looks like. A manometer looks like so. So say we've got a tank that is connected to a tube. Okay? And in this tube, we have some fluid. Right? All right, so there is the interface, say, at point B. Here is another interface at A. And this tank is perhaps has some pressure that we want to know. We want to be able to measure the pressure in this tank. Okay, so the pressure here is going to push on the fluid and make it rise up the tube. And we, of course, have atmospheric pressure pushing down onto the fluid. So simply, this pressure in the tank can be measured as the atmospheric pressure plus the static pressure associated with this rise in the fluid height. Okay, so if I can measure this length L, then the static pressure associated with this fluid rise L is going to be the density of the liquid times gravity times L. So if you do a dimensional analysis on these terms, you'll see, of course, pressure has units of pressure, and density times gravity times length also has units of pressure. A barometer works much the same way. All right, so here we're going to have a bath of fluid and an upside down tube that is submerged in that fluid. So I'll change color. So the pink will represent the level of the fluid. So maybe the fluid has risen to this height in the tube. Okay. And above here is vapor, and it is just the fluid's vapor. So if this were mercury, which was a common fluid used in barometers, then up top we've just got mercury vapor. And it's got an associated pressure, P, vapor. Okay, so on the outside, again, we've got pressure, ATM here. Our fluid has risen some height L. So the pressure of the atmosphere, and I'm going to write it as if we're solving for the pressure of the atmosphere because that was the purpose of a barometer, was to measure atmospheric pressure. So atmospheric pressure is going to be simply the pressure of the vapor plus the density of my liquid, in this case it's mercury, times gravity times the height of the rise of the fluid in the tube.